Justin Miller, Upstart College Physics here, and we are continuing on, as we generally do, right? So, talked about some potential difference due to, correlated with uniform electric fields and such things. I want to go off a little bit more and start talking about the potential difference due to fields that aren't uniform, that vary in direction, that vary in magnitude spatially. So, let's just get to this, right? Ooh, stuck with this. Excuse me, not E hat. Delta V, electric potential difference, when E hat is not uniform. And ultimately, we look at the expression for it, and it does involve a little integration, but for those of us not doing calculus, it doesn't really matter, but for us that are doing, it does. So I'll just go ahead and take a little bit of a look at this. We've got ourselves that delta V for a non-uniform field, still static, but just non-uniform spatially, is negative the integral from some initial location to some final location within that field of E hat dot dr hat. So we've got to integrate the field over the position that spans from some initial to some final location, and that gives us what the potential difference between those two locations is. So this can be easy or it can be, well, moderately difficult. It really just depends on the nature of the electric field. We're not going to look at super complex cases. We're going to look at a few specific cases of general interest, and one of them is, what is the potential difference between two locations in the presence of a singular point charge? So this is in general here. In general. Let us find the potential difference between two locations in the vicinity of a singular point charge. All right, so let us first just go ahead and say, hey, we got this point charge, right? We got some point charge. We'll just go ahead and say it's a positive point charge. It doesn't really matter. And we know what its electric field looks like, right? It's radially outward, and it gets weaker the further away we get from it. And that's basically that. Well, this one's a little bit suspect looking, as is this, but that's what happens when I start drawing out things really fast. Anyways, that's kind of what the field looks like. Again, it varies spatially in both direction and in magnitude. So what do we have here? We've got ourselves that E hat is equal to K sub E Q over R squared, and points radially outward, R hat. So there's the correlated vector for the electric field due to a point charge Q. Great. And what can we do with this? Well, let us start with something easy and just say, hey, let's just look along the x-axis, sort of make our own little coordinate system here that cuts through, say that that's x, that's y, the charge is centered at the origin here. And we will look at two locations along the x-axis and see if we can determine what the potential difference between those two locations is. So what happens if we go ahead and say there's some point A and there's some point B? Let me get rid of that x there. There's some point A and B there, and we want to know what the potential difference between those 2 points is. Delta V, A to B is equal to what? Well, first off, can we determine whether we should get a positive or negative potential difference? And the answer is, yeah, we can. Because really that's hinged on which way you're measuring it and which way the electric field is directed for that measurement. So the electric field along the x-axis for this positive point charge is radially outward that way. And if you're displacing or considering changes in position that are in the direction of the electric field, you are moving through a negative potential difference. So at very least, we know that the potential difference that we measure in going from A to B should be negative, saying that the potential at B is less than the potential at A. But really, we want to have some formal way of determining this. So, how are we going to do this? Well, let's go ahead and utilize this expression right here and see what we get out of this. So we're going to take that expression and we are going to change it a little bit to fit what we have going on here. So we can write this expression now as delta V is equal to the negative of the integral from, let's call it x sub A to x sub B, because those two are on the x-axis. And then we've got E hat dot, well, instead of calling it dr hat, we could call it dx hat. Because again, the changes in position along the x-axis. And furthermore, we can also write that just considering along the x-axis, that this E hat is k sub E q over r squared I hat. So we change that r hat that's, I don't want to say arbitrary, but is really dependent to something specific because we're constraining ourselves along the x-axis. So definitely I hat. And dx hat is dxi hat. So what can we do with this? Well, we can start to think about getting rid of that dot product, number one. So let's go ahead and do this. We'll stick that up in there, and we can write then that delta V is equal to the negative integral from x sub A to x sub B of k sub E q over, well, this r can also be changed to x because it's a distance away. So I didn't change that here, but I'm going to, because instead of r, it's just distance x. You have x on the x-axis, so we'll call that x squared, and that is I hat, and then we've got, that's dotted into dx I hat. Well, dx hat is dx I hat. So there we go. We've got an I hat dot I hat. I hat's parallel to I hat, right? So the angle between them is 0, and thus they just kind of vanish. I hat dot I hat is 1. So with this, we've got that this is then equal to the negative integral from x sub A to x sub B of k sub E q over x squared dx. Oh, that got pretty nice all of a sudden, right? So let us go ahead and check this out now. Well, k sub E and q are both constants. So we can take those out and write this as negative k sub E times q times the integral from x sub A to x sub B of 1 over x squared dx. And that happens to be a pretty easy integral to solve, right? Just think about x to the negative 2. What is it going to be? Negative x to the negative 1. There we go. So this is going to be equal to negative k sub E q times negative 1 over x evaluated from x sub A to x sub B. All right, well, the negative signs we can kind of cancel out here, and we can evaluate this from the limits and write this out as delta V A to B is then going to be equal to k sub E q multiplied by 1 over x sub B minus 1 over x sub A. All right, so that's what we end up getting out of this. Now, here's a question for you. We had said that the potential difference in going from A to B should be negative, right? Does that turn out to be negative? Let's think about this. It depends on what x sub A and x sub B are. Well, we have that in this correlation here, x sub b is greater than x sub a because it's further away, right? Well, 1 divided by a greater number is a lesser number than 1 divided by a lesser number, which is a greater number, if that makes sense. That is to say that 1 over x sub b is less than 1 over x sub a, which makes this quantity here end up being negative. So the end result would be that indeed, yes, we get ourselves a negative quantity and going from a to b. We switch the limits of integration, you go from b to a, now it turned out to be a positive quantity. That's okay, that's exactly what we want. The sign is in there, great. What does this allow us to really do though? Well, it allows us to, again, figure out what the potential difference is in the presence of a singular point charge between two locations, and it also allows us to define what the actual electric potential is at a specific region in space. That is under the assumption that the electric potential at infinity, yes, infinitely far away is equal to 0, which should make sense when you're when you're infinitely far away from this point charge. The electric field has gone basically to 0, and also the potential at that location should be equal to 0 as well. So under those limitations there, we can say that this is like delta V is equal to k sub e q over x sub b minus k sub e q over x sub a, which is equal to v sub b minus v sub a. V sub b is the electric potential at point B, and V sub A is the electric potential at point A. All right, this assumes that V is equal to 0 at infinity. Because really, we don't define true potentials, we define potential differences. Just like gravitational potential energy, we really define changes in it. Same sort of correlation here. But if we say 0 at infinity, then we can have a well-defined potential at regions in space. So, there's some things that go along with this. And what I want to do with this is ultimately look at those things. So let me come right back so I can erase some of this and start to redraw some stuff out. And I'll take over this time. Be right back. All right, so what do we want to do? We want to keep on going here and continue looking at the electric potential due to a point charge. So we just had it along the x-axis. Well, we could have done the same thing along the y-axis, right? And had like a y sub a and a y sub b. That would be fine too. But really, we could do it anywhere. So consider this. We've got ourselves, I grabbed the black pen. That's okay. We've got ourselves a positive point charge here. And what we want to do is draw what the surfaces of equipotential look like. So again, the electric field goes radially outward and reduces in its magnitude as we get further and further away. That's great. So what do the surfaces of equipotential look like? Well, the surfaces of equipotential are really based upon being the same distance away from the charge. And the surfaces have to go through this electric field such that they are perpendicular to the electric field at every given location. Well, if the electric field's radial, then what does the surface have to be like? The surface of equipotential have to be? It has to be spherical. So really what we get here for surfaces of equipotential is we could do a whole bunch of them or just a few, but these would be surfaces of equipotential. That is that there is no difference in terms of changes in potential energy or potential differences and having a charge, say, right here, or right here, or right here, because those are all the same radial distance away from this other point charge right here. We've got, say, A, B, and C. A, B, and C are all at same potential. Why? Because the magnitude of the electric field is exactly the same there, and to get from one of these points to the other, we can get there by having no overall displacement in the direction of the in the direction of the electric field. So that's it. That's really what correlates with surfaces of equipotential. There'd be no change in potential energy in taking a charge and moving it to there, or moving it to there, or anywhere along the surface. But the second you start moving this charge that way or this way, there is a change in potential energy. Thus, there is a potential difference between two locations. But as long as we're just going from A to B to C or to D, as long as we're staying on one surface or going from a point on that surface to another point on that surface, doesn't matter how we get there, right? We've moved through a zero potential difference. So, if I say I've got A, B, C there, and then we say over here, I've got a D, I've got an E, I've got an F. Well, we've got the D, E, and F are all at the same potential. Though it's not the same as A, B, and C. Because what? Because to get from, say, A to D or A to E or A to F, or anywhere on this one surface to anywhere on this surface, we'd have to have some displacement that is in line with the electric field. And thus, there would be work done, and thus there'd be a change in potential energy, and thus we'd move through a potential difference. So that's it. So here's the big picture of this. I can go from A to D, kind of like in that last example, and say, okay, there's a potential difference that I move through that would be the potential difference at A minus, the potential difference at D minus the potential difference at A, final minus initial. D would be at a lower potential than A because it's further away in the electric field, in the direction that the electric field's pointing, and that would be great. Can compute it out, and we'd go ahead and get that delta V sub A to D would be equal to V sub D minus V sub A, which would be equal to K sub E Q. We'll Q's this charge right here. Charge produced in the field. From K sub EQ over X sub D minus K sub EQ over X sub A. Because again, we could say that those are both along the x-axis. Well, this is going to be the same. Same as delta V and going from A to, well, E or F or throw in another one, G right above it. A to G. Why is it going to be the same? Well, because the potential at point G is the same as the potential at point D. So we would though have V sub G minus V sub A is equal to K sub E Q sub B Q over y sub D, y sub G minus essential K sub E Q over X sub A. Again, I'm using Y and X here because one's on the X axis, one's on the Y axis. But you may say, well, you can't mix X and Y up. I say it doesn't matter because this is what we could always do in moving from A to G. Is I could move from A to B because B is at the same potential as point A, and then consider going from B to G. And that would be exactly the same as going from A to G. I'd move through the same potential difference. Or I could go from A to D and then move from D to G. And moving from D to G doesn't change the potential difference. There is no potential difference between D and G. So what would happen? It'd be the same as just going from A to D. So that's kind of the big picture here, is that we can get to any positions on any surfaces by just considering the radial distance between the two surfaces themselves. It doesn't necessarily have to be, oh, what's the distance between this point and this point? Well, that's different than the distance between this point and that point. It doesn't matter, because all that we need to consider is the radial components, because the direction of the electric field is completely radial. And only displacements in the direction of the electric field or in line with the electric field will constitute any changes in potential, changes in electric potential. Only changes in position that are radial will result in non-zero potential differences. So we can write the potential difference at some radial distance away from a point charge, from the point charge Q. That's a big subscript, huh? That's just going to be equal to K sub E Q over R. R could be X sub A, R could be Y sub B, R could be whatever we want to call C, composite. But it's just the radial distance, that's it. So we'd have this is R sub A, this is R sub B, this is R sub C. We have R sub A is equal to R sub B is equal to R sub C. Thus they would all be at the same potential, and thus the potential difference between any of those 3 points would be equal to 0. So in the end, this is how we want to utilize, or how we want to represent, the electric potential at a location in the vicinity of a singular point charge. So for a singular point charge Q, the electric potential at a radial distance away from that charge, the potential at is given by, we've already written it, just going to write it again. V is equal to, I can write V sub Q, V due to the point charge, is equal to K sub E times Q over R. It's not a vector quantity. And notice it's very similar to what we had for the electric field, but it's not a vector. This is a scalar. And it doesn't go as 1 over R squared, it goes as 1 over R. So this causes people to make mistakes from time to time in terms of confusing the electric potential with the actual electric field's magnitude at some distance away from a point charge. Don't get them messed up. Don't get them messed up. Electric potential goes as 1 over r, recedes as 1 over r, and electric field recedes as 1 over r squared regarding a point charge. Some other things to note. This is an absolute value of Q. This is just Q. Q can be plus or minus. Plus charges produce plus potentials. So the electric potential in the vicinity of a positive charge is positive everywhere. It's the potential difference that can be positive or negative depending on whether you're going from high to low or low to high. And minus charges produce negative potentials. Still can be positive or negative in terms of the potential difference between two locations, but that's really dependent on which way you're moving. In the direction of the electric field, move in the direction, you'll be moving from high to low, thus through a negative potential difference, or moving in the opposite direction of the electric field from low to high, thus we'll be moving through a positive potential difference. All right, so that is awesome in itself, but what's even awesomer is what happens if we have multiple point charges. What do we do then? Whew. Well, it's a good question, right? We have multiple point charges. Just as the electric field adds up as vectors, the potential at a given location adds up as well. But it's much easier to add because it doesn't have a direction associated with it. So, what do we do then? We're just adding scalar quantities. And that is much more straightforward, adding up a bunch of vector quantities. One sec. All right, so now consider the potential at some location in the vicinity of 2 point charges. Q1 and Q2. All right, so what can we do? Hey, throw up a couple point charges and say, what's the potential at this point? What's the potential at this point? Electric potential is the scalar sum of the potentials due to individual charges at a given location. So we can take some Q1 and we can take some, doesn't really matter, Q2. If we wanted, we could draw on the electric field, but we already know if these are equal and opposite charges, it's just a nice symmetric dipole. If one charge has more than the other, then it's kind of a shifted or squished to one side dipole. Not really worried about the electric field now. What are we worried about? We're worried about what the potential is at a given location in space. So say that I want to know what the potential is. Let's do something like this. What is the net potential right there? Well, at any given region in space, there's only one potential. And it depends on what charges are in the vicinity of that position in space. So we would have that this sigma v at this point P, we'll say, sigma v sub P is equal to VQ1 at P plus VQ2 at P. So we just add up the individual potentials to those individual charges at that location in space. How do we do that? Well, we want to say very carefully, but that's kind of generally what we want to do is be careful. What do we have here? Well, we have that Q1 is some radial distance away from that point, which we could call R1. And Q2 is some radial distance away from that point, which we could call R2. Well, that makes things pretty easy because we've got ourselves that VQ1 at P is going to be K sub E Q1 divided by R1. All right. And then V sub Q2 at P is going to be equal to K sub E Q2 divided by R2. As long as we know what R1, R2, Q1, and Q2 are, and that's really all that we need, we can compute what the potential is at that location. So we would have that V at point P is our K sub E Q1 divided by R1 plus K sub E Q2 divided by R2. And we get some numeric value, right, in volts. Well, that's great. Great, we can get the potential at point P. What happens if we want the potential somewhere else? Like, some other point, let's do this. Want it at some other point, like over here. Let's call this PQR point, what do I want to call it? Call it point Z. Point, no, Z's not good either. X, Y, Z, PQR, let's call it point U. Point U, and we want to know what is the potential at point U. V sub U is equal to what? And we say, why do you want V sub U? Because maybe we want to actually know what the potential difference is between point U and point P. All right, so what do we have? Well, again, this was P there. We could go ahead and break out point U and say that sigma V sub U is equal to VQ1 at U plus VQ2 at U. And what's that going to be equal to? Well, figure out where I want to do this at. We'll just do this here. Well, we've got ourselves that we've got another R. What do we want to call this R? I want to call R1 again. So this is where you got to be a little bit aware of subscripting things nicely. So we've got this R and we've got this R. What do we want to call them? Well, once we stick in another point, it would probably be wise to call this like R1P, R2P, R1U, R2U. So we're referencing the charge, Q2, and the position in space in which we're trying to find the potential due to that charge to, which is point U. So I'm going to do that. We could change these little Q's. We'll change these to R1P, R2P, R1P, R2P. And then we can go ahead and say that. Like this. That V sub U is equal to K sub E Q1 over R1U plus K sub E Q2 over R2U. So we got the potential at two different locations in space. Great. What happens if we go ahead and say, what's the potential difference between point U and point P? What is delta V P to U? So the potential difference between those 2 points there. Now we want to know this. Delta V, P to U. So measuring it from here to there. Well, what's that going to be? That's going to be equal to the overall potential at point U, final, V sub U minus V sub P. What does that all equal? Well, we just go ahead and expand this all out, right? Oh, we got a common factor of K, so we'll just leave it, it's okay. We got ourselves a K sub E, Q1 divided by R1U plus K sub E, Q2 divided by R2U minus the quantity of K sub E, Q1 over R1P plus K sub E, Q2 over R2P. Notice it's minus this quantity, so it's really minus as we distribute it through. And what do? You calculate it all out. You got the potential difference between those 2 points. Great. And this is all symbolic, but you're getting the idea of what needs to be done here. You can ask one last thing. Say, hey, if we moved a charge Q3 from point P to point U, what would be the change in potential energy? Now, move a charge Q3 from point P to U. Find the change in potential energy of the system in doing so. So we'll assume that there's already we don't want to assume there's already a charge, but we take a charge and we put it at point P. Well, there's some little things to just kind of think about what happens if we do that. So first of all, we're going to assume that we can just take a charge and stick it at point P. And then we're concerned with what's the change of potential energy of the system in moving that charge from point P to point U. So what do we get here? Well, if we put a charge here, does that change the potential at that location? And the answer is no. No, because R would be equal, R3P would be equal to 0, because that's where the charge is. It's undefined. We don't want to say it's infinity, it's an undefined quantity. So putting a Q3 right here doesn't change the potential at that location. But it does change it at this location, because now we'd have 3 charges producing the potential here. Ooh, you may say, oh shoot, what? Well, but since this is a charge that we're moving, we're going to move it, and while we're moving it, the potential both here and there are both changing. But by the time we move it from here to there, when we put it right there, what's the potential at point U now when Q3 is right here? The potential due to Q3 at that location is, again, undefined. Thus, the potential at U, once Q3 is there, is still just the potential due to Q1 and Q2. So ultimately, what that's telling us is we don't need to consider how Q3 may be changing the potential spatially or in the vicinity of itself, because we're only concerned about the change of potential energy that occurs in moving that charge from this point to this point, where the potential at this point when Q3 is there is just due to Q1 and Q2, and the potential at this point when Q3 there is just due to Q1 and Q2. So Q3 ends up being irrelevant in terms of the potential that it produces. So in the end, when we answer this, how are we going to find the change of potential energy? Well, we go back to this, the definition of potential difference being the change of potential energy per unit charge. So the change of potential energy is going to be equal to the charge that we're moving multiplied by the potential difference that we move it through. So we've got Q3 is the one that we're moving. What are we moving it through? The potential difference between these 2 points. So we're moving it through the potential difference of delta V, P to U. That's it. If we know what Q3 is, we've already determined what delta VP to U is, being this quantity right here, determining the change of potential energy, snappy. But it is sort of intricate to think about how it doesn't matter if there's a charge at these two locations or not. If that's the charge that we're moving, because by the time we move it to that position, it's the same potential at that location as before. All right, so what we'll do is leave that as that. Come back and do a little problem with this. All right, you well.